This is section 4.2. Here's the warm-up, and there's the derivative. You can take a look at it. It's just a little bit of review. Give the intervals on which the function is increasing and decreasing. So this function is increasing on negative infinity to this x value right here, which is negative 3.12. And then it increases again after this x value right here, which is negative 0.214 to infinity. So that's where it's increasing. Now note that whenever a function is increasing, if we go left to right, the slopes are positive. And then the slopes of the curve become 0 right here at this local maximum. Then they become negative. The slopes of the curve are negative where the function is decreasing. So decreasing from negative 3.12 to negative 0.214. And then the slopes end up going to 0 at this local minimum. And then because this graph is increasing, the slopes then become positive. So a local maximum is where the slopes change from positive to negative. And then local minimums is where the slopes change from negative to positive. Mean value theorem. If y equals f of x is a continuous at every point of the closed interval, so continuous on the closed interval, and differentiable on every point of its interior AB, which is the open interval, then there is at least one point C in AB at which the instantaneous rate of change equals the mean rate of change, or the average rate of change. So what they're saying is if you averaged over a course of time 55 miles per hour, somewhere in there you were going 55 miles per hour. If that's what your average is, somewhere in there you were going 55 miles per hour. Now graphically we can say that average rate of change is the slope of the secant line. So somewhere the slope of the secant line, or this right here, is equal to the slope of the tangent line in that interval. Somewhere they're parallel. And that's what the mean value theorem says. Show that the function f of x equals x squared satisfies the hypothesis of the mean value theorem on the interval 0, 2. Then find a solution C to the equation. So there's two parts to the hypothesis. One, continuous on 0 to 2. Now, can we say that that happens? Yes. X squared is continuous from 0 to 2. So we can put a check there. Differentiable on 0 to 2, not including 0, not including 2. Well, f prime of x is equal to 2x. And there's nowhere in 0 to 2 where this would fail to have a value. So this is differentiable. 2x is, x squared is differentiable on 0 to 2. That's a check. So we satisfy the hypothesis. Now we're going to find out where f prime of little delay there, f prime of c is equal to f of b. F of 2 would be 4 minus f of 0, f of a would be 0, over 2 minus 0. Now we want to know where 2c, or the derivative, is equal to 2, and that's at 1. So here's the slope of the secant line. There's the secant line, and the tangent line that has a parallel, or the tangent line that's parallel to the secant line is at x equals 1. Explain why each of the following function fails to satisfy the condition of the mean value theorem on the interval negative 1 to 1. Well, if we graph this, f of x here equals the absolute value of x plus 1, because that's what the square root of x squared is. It's the absolute value of x. So the absolute value of x plus 1, that's up here, just like this. So this is actually continuous on negative 1 to 1. Yep, check. Is it differentiable on negative 1 to 1, not including those? No. There's a corner there, not differentiable at 0. So no. Not differentiable at x equals 0. What about this piecewise function? Let's plug 1 in here, and we get the point 1, 4. And if we plug 1 here, we get 1, 3. So this is not continuous on negative 1 to 1. It fails at an endpoint. It's not continuous at 1. Let f of x equal the square root of 1 minus x squared. That's the top half of a circle. Square root of 1 minus x squared. Point A equals negative 1 comma something. Well, if you plug negative 1 in here, you get 1 minus 1 is 0. So it's really the point negative 1, 0. And point B is going to be 1 comma something. Well, that's 1, 0. So 1, 0 is point B. That's right there. And A is negative 1, 0. That's right there. Find a tangent to f in the interval negative 1 to 1 that is parallel to the secant. So parallel to the secant, well, we know that's up here at x equals 0. That's parallel where the instantaneous velocity is equal to the average velocity, or the secant line is parallel to the tangent line. So let's find out that it's actually at x equals 0. We're going to take the derivative of f, which is 1/2 1 minus x squared to the negative 1/2, and then times negative 2x. The 2's are going to cancel. We get negative x over square root of 1 minus x squared. And we want that slope. This slope right here is 0. And we could even do 0 minus 0 over 1 minus negative 1, or y2 minus y1 over x2 minus x1, and we get 0 over 2, which is a slope of 0. So we want this slope to be 0. Well, how do we make a fraction 0? We make the top 0. So x equals 0 is where these two are parallel to each other. But if we plug 0 into the original function, 1 minus 0 is 1, square root of 1 is 1. So we get the point 0, 1. So the tangent line is y minus 1 is equal to 0 times x minus 0. So in other words, y equals 1. And we can see that the equation of that line is y equals 1. Physical interpretation. If a car accelerating from 0 takes 8 seconds to go 352 feet, its average velocity for the 8-second interval is 44 feet per second, or 30 miles per hour. So over this time interval right here, this slope right here is, what do they say, 30. At some point during the acceleration, the theorem says the speedometer must read exactly 30 miles per hour. So somewhere the exact velocity is the same as the average velocity. Increasing function, decreasing function. Let f be a function defined on an interval I, and let x sub 1 and x sub 2 be any 2 points in I. F increases on I if the previous x is less than the next x. So a function is increasing if the next x is bigger. And that's what this is saying. F decreases on I if the next x is actually, if x1 is less, and they turn it around, they turn this around right here. Then they're saying that if now the next x is smaller, then this function is decreasing. The mean value theorem enables us to identify exactly where the graphs rise and fall. So increasing and decreasing function. If a function is increasing, then the slopes of the curve are positive. If a function is decreasing, then the slopes are negative. Determine where graphs rise or fall. The function y equals x squared is a decreasing. Well, let's investigate this. And we can see that from negative infinity to 0, we have negative slopes. So the function must be decreasing from negative infinity to 0. And then positive slopes after that. So this must be increasing from 0 to infinity. Well, if we take the derivative is 2x, and we set that equal to 0. In other words, where is it neither increasing nor decreasing? Well, that happens to be at x equals 0. So now if we put that on a number line, 0, and we plug in some test points, let's say negative 1, and we test that point in the derivative. The derivative is negative, so this must be a decreasing function here. And over here at 1, if we plug 1 into the derivative, 2 times 1 is 2, that's positive. This must be an increasing function. So decreasing from negative infinity to 0. Why? Because the slope is less than 0. The slope is negative. Increasing on 0 to infinity. Why? Because the slope is, or the derivative is greater than 0. Determine where graphs rise or fall. Well, let's not pretend that we don't know what this looks like. It's an x to the third, so it looks something like this. Some version of an x to the third. So we know this function is going to rise and then fall and then rise. But we're going to find out, let's see, where is the function increasing and where is it decreasing? So let's take the derivative. That's 3x squared. This is the first derivative, not second. Minus 4. So if we set that equal to 0, 3x squared minus 4. If we set it equal to 0, we're finding out where the local maximum is. We're finding out where the local minimum is when we set this equal to 0. So 3x squared is equal to 4. X squared is equal to 4/3. And so x is equal to plus or minus 2 over the square root of 3. So I already know what's going to happen. This is increasing from 0, from an x0 to negative 2 over square root of 3, decreasing in between those two, and then increasing after 2 square root of 3, 2 over square root of 3. But let's do this on a number line. If we had negative 2 over square root of 3, and we have positive 2 over square root of 3, we got to test some points. So I know 0 is in between there. 2 divided by 1 point something is negative 1 point something. So I'm pretty confident with negative 2 over here. 2 divided by 1 point something is 1 point something. So I'm very confident with 2 here. So let's test negative 2 into the derivative, into this right here. 4 times 3 is 12. 12 minus 4 is positive. When we plug 0 in, we get a negative. And when we plug 2 into this, we get, again, 12 minus 4 is 8, which is positive. So we can see the function is increasing, then decreasing, and then increasing. So increasing from negative infinity to negative 2 over square root of 3. And then it increases again at 2 over square root of 3 to infinity. Now this is decreasing between those two values. Negative 2 over square root of 3 to 2 over square root of 3. Functions with f prime equals 0 are constant. If f prime equals 0 at each point of the interval, then there is a constant c for which f of x equals c for all x and I. So the derivative of constant is 0. This says if the derivatives of f and g are equal at each point of an interval I, then there is a constant c such that f of x equals g of x plus c for all x in I. So what they're saying is find the function f of x whose derivative is sine x. So the derivative is sine of x whose graph passes through the point 0, 2. So the function must be negative cosine, but then cosine of x, but then plus some constant, because the derivative of a constant is 0. So we could have we could have an infinite amount of constants, and this derivative would be sine of x. Well, now we know an x and we know a y. So to find c, we can plug those values in. 2 is equal to cosine of 0 plus c. 2 is equal to 1 plus c. So c is equal to 1. And so the function f of x is equal to negative cosine of x plus 1. It's called the antiderivative. So when you take derivative, you go from this to this. When you go backwards, that's called antiderivative. Find the velocity and position function of a body falling freely from a height of 0 meters under each of the following sets of conditions. It is assumed s of 0 equals 0 for a and b. The acceleration, so letter A, so a of t is equal to 9.8. That's what this says. And the body falls from rest. So that means the velocity at time 0 is 0. Well, this is 9.8 t, that plus c. So the body is falling from rest. So 9.8 times 0 plus c. So in this case, c is equal to 0. So v of t is equal to 9.8 t. And I think we're supposed to find velocity and position function. So now s of t is equal to 4.9 t squared, because 2 times 4.9 gives you 9.8 plus c. But it's assumed that the position is 0 at 0. So that's equal to 4.9 times 0 squared plus c. So c is equal to 0. So the position function is 4.9 t squared plus 0. Letter B, we start out the same way, where the a of t is equal to 9.8. The acceleration is 9.8 meters per second squared, and the body is propelled downward with an initial velocity of 1 meter per second. So the velocity, v of t, is equal to 9.8 t plus c. But the initial velocity at time 0, at time t equals 0, is 1. So the velocity is 1 when the time is 0. So c is equal to 1. V of t is equal to 9.8 t plus 1. S of t, position, is 4.9 t squared plus t plus c. So that's the antiderivative of this. And it's assumed that the position is 0 at time 0. So c is equal to 0. So s of t is equal to 4.9 t squared plus t. State whether or not the function satisfies the hypothesis of the mean value theorem on the given interval, and if it does, find each value of c in the interval, ab, that satisfies the equation. So let's do by hand, and then we'll look at the graph. What am I doing? State whether or not the function satisfies the hypothesis. So continuous on 0 to 1. Yeah, check. Differentiable on 0 to 1. Well, we don't know the derivative yet. So f prime of x is equal to 2/3 x to the negative 1/3, or 2 over 3x to the 1/3. Well, x can't be 0 now. X is the derivative is undefined at 0, but it doesn't have. It's okay to be at 0. It's okay to be at an endpoint. So that's a check. Yes. So now 2 over letter B. What am I doing? Letter B now, right? B. Find the value of c. 2 over 3c to the 1/3 is equal to, let's see, f of 1. 1 to the 2/3 is 1, minus f of 0, which is 0, over 1 minus 0. So 2 over 3c to the 1/3 is equal to 1. Let's multiply this over. 2 equals 3c to the 1/3. So c to the 1/3 is equal to 2/3. And so c is equal to, I'm going to raise that to the 3rd power, 8 over 27. Let's look at the graph, I suppose. Clear this. Quit. Let's go y equals. Clear x to the 2/3. Thirds graph. Oh, I should change this window. And we're really looking from 0 to 1. So 0 to 1. So the slope of this secant line, is the same as the slope of the tangent line at 8/27. At 8/27. Talk about the graph. Okay, let's talk about the graph. One to the right. This is what the graph looks like. So we can say continuous on 0 to 4. Check. Differentiable on 0 to 4. No, not differentiable at 1. And so we move on. Find where the extrema occur. So we're going to go f prime of x is equal to, oh, by the way, this is an x to the 3rd, so this graph looks something like this. Let's take the derivative. We got x squared minus 2x minus 3. We're going to set that equal to 0, so we're finding out where these local mins and local maxes are, where the slope of the tangent line is 0. plus 1. So this is happening at x equals 3 and x equals -1. Find where the extrema are. And then if we didn't know what the graph looked like, we would put these on a number line. We'd go -1, and we would go 3 over here, and then we get some test points. How about -2, 0, and 4? So if we plug -2 in, we get negative times a negative, that's a positive, which says that this is an increasing function from -infinity to -1. When we plug 0 in, we get a negative. That means that this function is decreasing. And then if we plug 4 in, we get a positive times a positive. That's a positive. So increasing, decreasing, increasing. Find where the extrema are. Well, this now is a local maximum, local max. Local max at x equals -1. And this is a local minimum because the first derivative changes from negative to positive. So local minimum at x equals 3. Use analytic methods to find A, the local extrema, B, the intervals on which the function is increasing, and C, the intervals on which the function is decreasing. So let's go G prime of x is equal to 2x minus 1. So we'll set that equal to 0. 2x minus 1. 2x equals 1. X equals 1/2. So let's put 1/2 on a number line. 1/2. There's the critical point, we call it. And 1 is over here and 0 is over here. Now if we plug 0 into the derivative, we get -1. So this is a decreasing function. And then if we plug 1 in, we get 2 minus 1, which is positive. Now it's an increasing function. Well, this is a parabola. This is a right side up parabola. So yeah, they decrease and then they increase. And what we found was the local minimum because the slopes are going from negative to 0 to positive. So that must be a local minimum. So we have actually not only a local minimum, a global minimum. So minimum, let's see, work these analytically and then look at the graphs on the calculator to find the local extrema, the intervals on which, okay, so the local extrema. Minimum at x equals 1/2. And we are, let's see, decreasing on -infinity to 1/2 and then increasing from 1/2 to infinity. Number 18, we got k of x is equal to 1 over x squared. So that's really x to the -2. So the derivative is equal to -2x to the -3, which is equal to -2 over x to the 3rd. So this derivative is undefined at 0. That's a critical point. So critical points happen where the slope is 0 or where the slope is undefined. So we have a number line. We're going to plug in -1. We're going to plug in 1. So when we plug in -1, we get a negative over a negative, which is a positive. So we have an increasing function. Then when we plug 1 in, the derivative is negative, so we have a decreasing function. So it looks like we have a local maximum here. But the domain of the original function, the domain, is -infinity to 0, union with 0 to infinity. X can't be 0. There's actually a vertical asymptote at 0. So you can't have a local maximum or a minimum where you have a discontinuity. So there's, even though it looks like there is a local maximum here, there isn't. Now, functions can change whether they increase or decrease over discontinuities. So this is still useful information. But A is find the local extrema, none. There's none. B, increasing on -infinity to 0. And then C, decreasing from 0 to infinity. So if we look at the graph here, 1 divided by x squared, we notice that there is a vertical asymptote. So increasing vertical asymptote, and then when you get to the other side of the vertical asymptote, this function is decreasing. And then you're asked to upload this to Google Classroom.